IGCSE Cambridge Computer Science O-Level Paper 1 for the session May-June 2025. Question 1. The size of a file can be measured using different data storage units. Tick one box to show the smallest data storage unit. So a byte is basically 8 bits, right? A gigabyte, okay, is basically a billion bytes, right? A kibibyte, okay, is around a thousand bytes, right? And a gigabyte is around a billion. That means one with 9 zeros next to it. And a nibble is 4 bits, which is half of a byte. So we have half of a byte, 1 byte, around 1,000 bytes, and around a billion bytes. So the smallest data storage unit is a nibble. State how many tebibytes are equal to 2 pebibytes. So we have a normal byte, right? And then we have a kibibyte, and then a mebibyte, and then a gigabyte, and then we have a tebibyte, and then we have a pebibyte. By then I mean a multiple of 1,024, multiple of 1,024, multiple of 1,024. So 1 tebibyte, right? If you want to convert from a tebibyte to a pebibyte, right? A pebibyte is 1,024 tebibytes. So that's 1 pebibyte. That's 1,024 tebibytes. So if you want 2 pebibytes, that will be 1,024 multiplied by 2, which is of course 2,048. No calculator needed. So that is the final answer. 2 pebibytes are equal to 2,048 tebibytes. For part C, the size of a file needs to be reduced. Give the name of the process that is used to reduce the size of a file. That's of course data compression, right? So compression, which of course we have 2 types of compression, lossy and lossless. One reason the size of a file may need reducing is so that it has a shorter transmission time. Give one other reason why the size of a file may need reducing. We have multiple reasons. Firstly is less bandwidth. Bandwidth is basically how much internet consumption it takes to transmit that file over the internet. All right. Another reason is less storage needed to store that file, right? So we have multiple reasons, but of course you have to only state one. When they ask you to state one, you must only state one. And this is a 1 mark question. That means that only one answer is needed. Okay. So for question 2, a clothes store has a ticket system to allow customers to speak to a personal shopper. The ticket displays a ticket number in hexadecimal. For example, 11B, right? This is a hexadecimal number. The ticket system has an output device that creates a paper ticket. Identify an appropriate output device to produce the paper ticket. So what output device do we know that could produce a paper ticket? Well, of course, it's not a keyboard, right? Or a mouse or anything like that. It's, of course, a printer, right? A printer produces paper tickets. So for part B, each ticket number is stored as a binary number in the ticket machine. 2 ticket numbers are 14B and 97A. Convert the 2 ticket numbers from hexadecimal to binary. So let's take 1, 4, and B. So let's make a quick key. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Okay, this is just a quick key for those who do not memorize the letters, right? We know that a 0 in decimal is a 0 in hexa, a 1 in decimal is a 1 in hexa, right? However, when we start reaching anything after 9, some people get confused. So this is a quick key. So B is basically 11. And how do we write 11 in binary? So 11, what is the highest power of 2 that's lower than 11? It's 8, of course. The powers of 2 are 1, 2, 4, 8, 16. 16 is greater than 11, so we don't need it. So 8. So we subtract 8, and that is, of course, 3. And then we subtract 2 and the 1, right, to get the 0. So we use the 8, the 2, and the 1. So we put a 1 over the 8, 1 over the 2, and 1 over the 1, and 0 here, because we did not use the 4. So a B is 1, 0, 1, 1, right? 4 is, of course, 4. We only need to subtract 4. So 4 minus 4 is equal to 0. When we reach 0, we know that we're done. So we only used 4. The rest is zeros. So 4 is 0, 1, 0, 0. 1 is very simple too, because we only need to subtract 1, right? We only need to subtract 1 to reach the 0. So we only use 1, 0, 0, 0. So this is 1, 0, 0, 0. So this is basically the the binary number for the hexadecimal number 14B. It's 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, right? Now let's leave the key and go over to the second number. So 9, 7, A, right? We plot each one individually. 9, 7, and A. A is 10. How do we get 10? Well, we subtract 8, right? So we're left with 2, and then we subtract 2, we're left with 0. So we use the 8 and the 2. So 1, 0, 1, 0. 1, 0, 1, 0. So for the 7, we cannot subtract 8 from the 7. It will be a negative number. So 7 minus 4, we'll get 3, minus 2, we'll get 1, minus 1, we'll get 0. We use the 4, the 2, and the 1. The 4, the 2, and the 1. So 1, 1, 1, 0, right? So for the 9, we will subtract 8, and then we will subtract 1. So we use the 8 and the 1. So 1, 0, 0, 1. 1, 0, 0, 1. So the final answer would be all of these binary numbers combined. 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, 1, 0. Okay, it's very simple. Now, for part II, give 2 reasons why the ticket number is displayed as hexadecimal instead of binary. Now we have many reasons for hexadecimal, and this question could come in many ways, but the reasons are always the same. For example, it's easier and quicker for people to read it and understand it, right? And it takes up less space, right? So less space and easier, right, to read, okay, or understand. Or if this was a programmer instead of the guy that will read the ticket, we would say easier to debug, okay? So part C, the ticket numbers could also be represented as denary. Convert the 2 ticket numbers from hexadecimal to denary. Okay, so simplest way to convert from a hexa number to denary is simply converting from hexa to binary and then from binary to denary. So we could do that quickly. 0, 2, and C. If we go back up, the C is basically a 12. Okay, and a 12 is basically minus 8. This will give us 4, and minus 4, this will give us 0. So we only use the 8 and the 4, so 1, 1, 0, 0. A 2, we only use the 2, so 0, 1, 0, 0. And a 0 is basically a bunch of zeros. Now let's convert this entire binary number into denary. What are the values? 1, 2, 4, 8, 16, 32, 64, 128. We don't care about the rest, they're only zeros. We only count the ones. So we count this one, it's 32. We count this and this. So 32 plus 8 plus 4. 32 plus 8 is 40, plus 4 is 44. So the first number is 44. Okay, and we repeat the exact same process for the other number. We repeat the exact same process for the other number. So 10b, right, or 10b. What's a b? B is 11. So for 11, we subtract 8, we left 3, and then we subtract 2, and then we subtract 1 to get 0, right? So we use the 8, the 2, and the 1. So 1, 1, 0, 1. A 0 is basically 4 zeros. And then we have a 1, which is 1, 0, 0, 0. What are the values? 1, 2, 4, 8, 16, 32, 64, 128, and this is 256. We don't care about the rest, they're zeros. So we take this 256 and we add it to this 8, and we add this 8, we add this 2, and we add this 1. So 256 plus 8 plus 2 and plus 1. So if we add these four numbers, we would get 267. Okay, 267. And that is our answer, 267. Okay, so for part II, we need to convert the two denary numbers into hexadecimal. The denary numbers are 1, 0, 9. So the powers of 2 are 1, 2, 4, 8, 16, 32, 64, 128. We need the largest power of 2 that's just below 109. So that's 64. So if we subtract 64 from 109, right, we'll get 45. We'll get 45, and we'll put a 1 over the 64. We can subtract 32 now, right? We could subtract 32, and that will give us 13, right? We put a 1 over the 32. We cannot subtract 16, so we subtract 8. We subtract 8, and that leaves us with 5. We use the 8, and 5 is basically a 4 and a 1. So minus 4 and minus 1, and that's 0. So a 1 over the 4 and a 1 over the 1. So our number is 10110110, which I basically just copied this number, the ones, and filled in zeros for all the digits that we did not use. Now we have this binary number, we can convert it to hexadecimal. So if we just split it into 4s, right, and this is basically 1, 2, 4, and 8. So 8 and 4 is 12, and 1 is 13, and the 13, of course, is a D, right? So this is a D. This is 1, 2, 4, 8. We do not count that. We count the ones. So 4 plus 2 is 6. So our answer is 6D. Okay. So for the other number, we will basically just follow the exact same steps. So for 415, okay, 415, we will basically subtract. We have more powers of 2, 256 and 512, right? 512 is too large for us, so the largest power of 2 that's just below 415 is 256. And if you just do some quick maths, 415 minus 256 would be 159. So we basically used this. Now we can subtract 128 from this number, so that would give us 31, right? So we subtracted 128, now we have 31. Now if you keep on subtracting, you will actually use the 16, the 8, the 4, the 2, and the 1. Okay, but a quick trick in binary is that if we have, for example, 1, 2, 4, and 8, right, and we represent that in 4 bits, if we want to represent the 7 right? Which is just 1 under the 8. It's basically everything ones except for the 8, right? If we want to represent a 3, which is basically just 1 under the 4, it's everything ones except the 4 is 0. If we want to represent 31, it's basically everything ones except the 32 is 0, right? So 1, 2, 4, 8, 16, yeah, 32. So this is how we represent 32. So if this is how we represent 32, this is just a quick trick, okay? This is just a quick trick. So if this is how we represent 32, that means that we will use the 16, we will use the 8, we will use the 4, we will use the 2, and we will use the 1. That means that our number is 1, 2, 4, 8, 16. We did not use the 32 nor the 64. We used the one with 28 and the 256. So this is our numbers. Let's split it into 4s, and we have an extra digit. So what do? We fill in zeros to make the third 4. Okay, so 111 is basically 15, which is an F in hexadecimal, right? So this is an F. 1, 2, 4, and 8. So 1 plus 8 is 9. 1 plus a bunch of zeros is just 1. So our final answer is basically 19F. Okay, so pretty simple stuff. This trick, well, you could use it if you want to. It makes life easier for you. And you could just keep subtracting the old way, but I definitely recommend understanding this method. So for question 3, an image is converted to binary to be represented by a computer. Complete the table with the missing terms and definition about representing an image. So this is the smallest component of an image. Well, the smallest component of an image is always the pixel. An image is just a bunch of pixels, right? So a pixel. In terms of the resolution, it is, well, the number of pixels, right? This is a bitmap image. The resolution is basically the number of pixels on the width multiplied by the number of pixels on the height, right? So this is the resolution. So this is the number of bits used to create each color in an image. So a bitmap image is consisted of pixels. Each pixel is consisted of a byte or a binary value, which is basically representing the color of that pixel. And that value is called the color depth, right? That's the color depth. So this is additional data that is stored with an image that can provide information such as the time and date the image was taken. And of course, that's the header of the bitmap image file. Okay, these are what a bitmap image file is consisted of. So question 4, a restaurant has an electronic ordering system. The system allows customers to select the food they want to order. The data for the order is transmitted across their network to a computer in the restaurant kitchen. The data is sent using serial full duplex data transmission. Give 2 reasons why serial full duplex is a suitable data transmission method for the data. So firstly, when we're talking about this type of data transmission, we are talking about traveling long distances, right? This is the first thing that comes to mind. And we have a less chance of error. Okay, we only need 2 reasons here, so these are some of the 2. There are some other reasons. For example, it makes sure that the bits arrive in order. Any other examples would be correct. Okay, these are just 2. Give 1 improvement that would be made to the data transmission if parallel transmission is used instead of serial transmission. And of course, that just means that the data will be transmitted faster, right? Faster data transmission. That's it. So now for part B, a checksum is used to check the data for errors after transmission. Describe the process of the checksum error detection method. So basically, what is a checksum? Firstly, we need to identify the steps. So firstly, the checksum is calculated, right? It's calculated using the data that it has using an algorithm. Okay, so the algorithm is applied on the data that it has to calculate the checksum. And then the checksum, right? The checksum is transmitted with the data, right? With the data that's sent. And the value is calculated again by the receiver, right? The value is calculated again by the receiver after the transmission. And if the checksum value do not match, then we have an error. If they do, well, then we're golden. And these are basically the steps that you need to mention, okay, when we're talking about the checksum. This is a 5-mark question. So everything I just mentioned was keywords. If you just put in any 5 of those keywords, you will get the full mark. By keyword, I mean the entire phrase, right? So, for example, a checksum is calculated is 1 mark, right? So make sure you put in at least 5 of those keywords. So part II, identify one other error detection method that could be used to check for errors in the data. Of course, we have a bunch. For example, the parity, the parity check, or the echo check. Okay, so for part C, a customer can also order food from home using the internet. The data for their order is broken down into packets and transmitted across the internet to the computer in the restaurant kitchen. Tick one box to show which item would not be included in a packet's header. Okay, so the destination address, well, that's of course included in the packet's header, and the originator address, right? So the sender and the receiver, both of their addresses are contained in the packet. The packet number, of course. The payload, it has nothing to do with this entire process. So this is not included in the packet header, and that's what the question wants. All right. So for part II, the packets of data may need to be reordered when they arrive at the computer in the restaurant kitchen. Explain why the packets of data may need to be reordered. So the packets may need to be reordered. Firstly, if the packets arrive in wrong order, right? This might be a reason. Another reason is that some packets might not arrive, right? Some of them might not arrive, so they might need to be reordered. 2 keywords or phrases are sufficient for this question, as this is a 2-mark question. For question 5, data is processed by the central processing unit, which is a CPU, in a computer that has a von Neumann architecture. Complete the table with the missing terms and definitions about processing data. So, what's the definition of a CIR, or a current instruction register? And this is basically simple. We can deduce the definition from the name. It just stores, right? It's a register, so of course it stores something. It stores the instruction, right? That's being executed, right? So it's storing the current instruction that's being executed. Very simple. This is a processing unit with the CPU that can fetch, decode, and execute instructions, right? So this is the core of the CPU. This is a list of all commands that can be processed by the CPU, and this is of course the instruction set, right? And the instruction set is basically a list of commands, and each of these commands has a single job that does help in the von Neumann architecture, right? It either fetches, decodes, or executes some data. The cache, well, it stores, right, frequent, you have to put in frequent or frequently used data, right? Used data. And the accumulator basically stores the result of interim calculations. Okay, so stores result of interim calculations. Okay, this is the job of the accumulator. These are simple definitions of the components of the von Neumann architecture. So for part B, identify the component in the CPU that is responsible for decoding and instruction. And that's, of course, the control unit of the CPU, CU for short. Explain how the clock speed can affect the performance of a CPU. Okay, so for each clock pulse, so the clock keeps ticking, right? Ticking, ticking. For each clock pulse, we have one cycle, right? So we have to explain this process, okay? And the clock speed is the number of cycles performed per second, okay? So if the speed of the clock is increased, the performance is increased. You have to explain this idea to them. It's a 3-mark question. Just any of these three keywords would suffice for this question. Okay.